Welcome to MLOps Live, a podcast by Neptune AI.
We host in-depth discussions where machine learning practitioners answer questions from other practitioners about one subject related to production machine learning and MLOps.
Tune in to get real-life stories, dirty hacks, and pragmatic workarounds from ML people in the trenches. So Mateusz has held a number of leading machine learning positions at companies like NetGuru and Brainly. So Mateusz, you have a background in computer science, but how did you get more into the machine learning side of things?
Yeah, so it all started on my sophomore year at university. One of my professors kind of told me about that Andrew Ng was doing his first iteration of the famous course on machine learning on Coursera. And I kind of started from there, then did bachelor thesis on deep unsupervised learning and went to Siemens to work in deep learning. And then all my positions were strictly about machine learning.
And you've been on that path ever since.
Yeah, exactly. I worked for some time before as a backend engineer, but for most of the time in my career, I was a machine learning engineer / data scientist.
Excellent. We'll be getting into the questions soon. This is a totally interactive Q&A session, and if you're here at the event present in the call, you can participate by raising your hand here in Zoom, and we will unmute you and you can just ask your question live if you want. You can, of course, also type the question in chat and we will pick it up from there. And if we have time, we will be going through any community submitted questions as well, submitted in advance. So also a reminder, this is going to be published as a podcast episode later on, so you can catch up with it later as well. So Mateusz, to warm you up, how would you explain to us pseudo-labeling in 1 minute?
Okay, let's try. So imagine that we're having lots of data and just small amount of data is labeled and most of that data is unlabeled. So, and we want to train our favorite neural network, let's call it ResNet50. And in simplification, we train the model on a batch of labeled data. And then with that model, we predict labels on batch of unlabeled data. We use the predicted labels as the targets to calculate loss function of unlabeled data. And we combine the loss from labeled and unlabeled data to backpropagate through the network and update weights. And this way, we leverage the unlabeled data in the training regime. Was it 1 minute or longer?
Yeah, nice job. I think that definitely fit inside inside 1 minute.
I have also I can give you one analogy to the computer science development process, how one could think about this. So let's say we have a software development team, and there are few senior engineers and bunch of mid-junior engineers. And senior engineers produce better code quality, obviously, than juniors or mids, but you can hire just a limited number of senior engineers, and you need and you also want to grow the mid and juniors, so you need to kind of construct a team of both and make it efficient. So if you invest into code reviews and best practices testing, automated CI and CD, then junior engineers are also able to deliver code to production as well. So you can think that senior engineers are the labeled data here, and the junior engineers refer to the unlabeled, to the pseudo-labeled ones. And investing into the code review is like scaling the loss function. So at the beginning of training, you need to invest more. So actually you care more about the labeled data. But once the network starts to make good predictions, you also benefit from the unlabeled data. So from the junior and mid engineers when your development practices are very solid.
All right. Thank you for that analogy. I'm sure this will prime everyone's minds nicely for any questions. So once again, welcome everyone. Have fun. And over to you, Stephen.
Awesome. Thanks so much, Mateusz. And of course, as you mentioned, you're currently in Brainly as a senior machine learning engineer. And I sort of presume, as we get to know, of course, that's where most of these applications are, coming. And I'd love to know, can you walk us through some of the different use cases where you apply pseudo-labeling for image data in Brainly. Some of the products, I know Snap2Solve is one of the products that probably uses it, or you probably have more idea. Yeah.
Sure. So the Snap2Solve is the feature my team works mostly around that feature, and maybe I'll shortly explain what it's about. So basically, when you open the mobile phone, you can make a quick image of the question you would like to have answered. Then, as a user, you can adjust the crop to select the question, and then you're routed to the either text search or our math solver, depending what's on the image, and you're getting the answer you needed. And our team works on projects like understanding what's on the image, understanding the layout of question, detecting the quality issues with the image, so trying to inform users that they could improve somehow the image they taken to get better answer, and also on that routing to the specific services that are needed for the question. So for example, if there's math, it can be, instead of just searching through the database, it can be directly solved, for example. And last year we had a project called Vice, which was about the visual content extraction. And in that project, we wanted to understand the layout of the question. And it was simply an object detection model that tried to predict classes like table, question, image, figure, text, and so on, everything that's kind of visible on the question layout. And the thing is, you always have a limited budget for labeling, even if you have a strong budget, a strong company, big company, not a small startup, then it's always limited. Also not about the money, but also about the time. How much time can you actually wait for the labels? And at Brainy, we have lots of images taken from the users. And we would really like to leverage all of that unlabeled data. And also, when you want to start labeling, for the training purposes, you would like to have more or less balanced distribution. So you would like to have the similar amount of the text boxes and the table boxes and so on. But your data is obviously very imbalanced usually. So our first approach to reusing self-supervised learning was to actually do some unsupervised or semi-supervised classification to generate data for labeling, to downsample the data from all of the images we had, so we could label for the training purposes only small subset, which would be still uniform. And in that project, we work on the paper called Simple Contrastive Learning. And on top of that paper, there are two frameworks for unsupervised classification called SPICE and SCAN. And Simple Contrastive Learning is basically about contrasting two images with one against the other. And you do it by you taking the original image and you do the dot augmentation, perturbation of the image. And you do two perturbations of the same image. So as an input, you have different images, but you know they're the same. And you learn the similarity of these images. And as a result, you get the good embedding for that image. Based on that embeddings, having very small amount of label data, we could actually sample very well, training weak classifiers to finally obtain good candidates for labeling. So that was our first, in our team, approach to self-supervised learning. Pseudo-labeling is a kind of interesting case in our situation, since in the original paper, it's the same network that generates the pseudo-labels. We go a bit different way, since in our case, we have multimodal inputs sometimes. So we have text and image, but not at all stages we have text. So sometimes we just need to deal with the image. However, when creating a data set and when training, we might reuse the historically available text. So we kind of use the NLP-based approach to generate pseudo-label that for the model that will then work in the production for the inference only on the image.
Awesome, thanks. And by the way, if you want to learn how Vice works, we did a case study with Brainly So I think that will probably be in the show notes for our listeners or attendees. So if you want to learn how Vice works and Snap to Solve, I think that will throw more light. Now, Mateusz, before Brainy, did you have any experience working on pseudo-labeling, and how was that for you? What applications were you building at that time?
Yeah, I had actually just when that paper came out. Paper is, I think, from 2013, and in 2014 I worked in a small startup in Krakow, and we did small projects for small startups. And there was that startup that was doing smart dog collars, and the smart dog collar was equipped with sensors like accelerometer, gyroscope, thermometer, and so on. And the goal of our machine learning system was to predict the behavior of the dog. So whether the dog is eating, drinking, or running. So later on, we could automatically send some tips to the dog owner that, like outside there is high temperature, and the dog didn't drink water for a long time. So imagine getting the data from sensors is easy because you just, put that dog collar on dog, but labeling that data, that's a very difficult one. And it's a funny story how we actually label that. There are these people who, for the job, they take a lot of dogs out. So we just connected with these people, and we went with lots of people multiple times with the dogs, and we are just noting that from 210 to 215 the dog was drinking and so on. And that's not really feasible way to gather a lot of annotations, but it was easy to gather a lot of unlabeled annotations. And since we suffered very much for overfitting, as far as I remember, we explored that pseudo-labeling angle at the time, and it's helped a lot to tackle the overfitting problem for that model.
Awesome. That's awesome. Thanks. I think someone has asked a question in the chat.
Someone wanted to get Mathieu wanted to get the title link to the paper that was mentioned.
The simple contrastive learning or pseudo-labeling.
And can you name an author?
The pseudo-labeling original paper was Dong Li, I think it's from 2013. Pretty sure we can add it to the notes later on.
Right. Yeah, we'll make sure to add it to the show notes, and I'll try to dig it up in the meantime. If we haven't, we have actually a question in chat from Antonin, who says, "Hey Mateusz, how did you choose the image augmentation to train your SSL model? Did you use the one from the paper, or did you experiment to find augmentation that suited your data the best?"
Yeah, I explored I started with exploring the data augmentations from the paper, so exactly that scheme. I also tried different kinds of augmentations, and I remember that the setup slightly differed for us, since our domain is really different actually than ImageNet, so it's reasonable that it's something different. So for example, we don't do flipping, because you shouldn't flip the text, at least not in English. But I explored. I used NVIDIA DALI for the data augmentations on GPU. So pretty much I explored all the typical augmentations that are in that library. And I know that, for example, in the augmentations there are much more to be explored, but it's slower. So usually I stick to the NVIDIA DALI one.
Awesome, thanks. Awesome. And and speaking of the challenges, and I would sort of want to know, were there challenges you sort of encountered when you were applying, say, self-supervised learning or the pseudo-labeling in your applications in Brainy?
Sure. So with the simple contrastive learning, so this algorithm that requires really lots of data, and even 1 million images, I think it's not really easy to train that algorithm. And obviously at Brainy we have more, and we can train on more amounts of data, but also training takes a lot of time, and projects has its constraints. And finally we ended up that the pre-trained embeddings on the simple contrastive learning weren't really much better than just the pre-trained on ImageNet. And it was more about that task of choosing the candidates for labeling. The most important part was actually trying something simple like support vector machines on that pre-trained embeddings and retuning them with Bayesian optimization for hyperparameter search. And that worked well for the most difficult cases. So in general, for tuning the simple contrastive learning, I think it requires very much computational power, a good way to distribute the algorithms, and also it requires pretty much big batch sizes from what I remember at the paper. They trained it originally on the bunch of TPUs, and the paper is, I think, from Google also. It's not as easy to reproduce everything what's on the TPUs with the size of you are constrained, for example, on the GPUs sometimes, and in terms of the memory size and the batch size. So these are challenges I see there. In terms of pseudo-labeling, it's kind of different. So usually you have a very small label data set. And if it's too small to learn the underlying cluster structure that can separate noisy but the initial examples, you just adding noise to your data when you're adding the more and more unlabeled loss coefficient when you increase that. The first problem could be a small labeled data set. The next one is, so when you do the pseudo-labeling, you have that loss function that is weighted combination of the loss from labeled data and loss from the unlabeled data. And usually you start with the zero loss from the unlabeled data, and you like to warm up your neural network on the labeled data. And you could start increasing the loss function from the unlabeled too fast, for example, and it would, before it actually learns the cluster structure. Also, in neural networks, there is usually phenomenon of overconfidence. So the predictions are very close to 1, for example, or very close to 0. And especially when you do the pseudo-labeling and the prediction obviously is sometimes incorrect, it also reinforces that phenomenon and adds even more noise to data. There's something called like confirmation bias then, and you need some techniques to tackle that. Usually it's done by applying mix-up strategy. So it's a strong data augmentation combined with label smoothing for regularization purposes, and that's something that can mitigate that confirmation bias.
Awesome. Thanks for sharing that. And I'm sort of wondering, because in this case you were talking about you applying it. Is this particular sort of application something that a small team can apply, or requires in terms of like resources? Just can you walk us through how tedious it will be for a small team to start applying this, especially when they have smaller data sets, because this is where it's more relevant, right? Where they don't have Google-sized data sets. Yeah,
so I would say that techniques like simple contrastive learning, which in general self-supervised techniques, they usually require a lot of computation, a lot of GPUs, and that's definitely difficult for the small team or just individual working on if has no access to the proper infrastructure for that. I don't think that these techniques are the best for the small teams. Probably the pre-trained models still work better. Also, the models that are trained self-supervised also are sometimes published. And there is actually a great library on the MIT license from Facebook on self-supervised learning. It's very easy to reuse. It's built on top of PyTorch. But the pseudo-labeling, it's something that's very easy to implement. And it can be really useful for fighting or overfitting and regularizing your network and making it work when you have a smaller data set.
And when applying that, have you particularly seen common mistakes that teams would make when trying to apply pseudo-labeling, or maybe even going further and trying to apply self-supervised learning techniques for their systems?
Yeah, so typical problem in the pseudo-labeling is when your small amount of data is not enough to satisfy the cluster assumption. So there is assumption that the data is separated well, and the decision boundaries in the low density regions. So it's basically that idea that the images that are close to each other, and they are in similar cluster, in same cluster, they share the same label. And if you don't have enough data to learn quickly underlying cluster structure, not maybe optimal, but good enough for this pseudo-labeling, then you end up with just adding noise to the data. Also, you might do everything well, but your initial small data set might be inconsistent. And inconsistency in labeling is something that hugely influences the quality of pseudo-labeling or training at all.
Perfect. Thank you. And I'm so wondering, because I'm going to come back to the use case of Brainy now, because what Snap to Solve is one of those products that enthuses me a lot. And I want to know, did you try out some other techniques, before the self-supervised learning technique, or did you just know that, okay, this particular technique is the one that we feel works, and then you just applied it straight away? Or how does it stack up with against other techniques, pretty much?
Yeah, so in general, most of the techniques we use is still supervised learning, and we label data, but it's limited and it's time consuming. And the best use case for us for applying self-supervised learning is when we want to downsample from all of the data we have for the labeling. So we make sure that we actually want to make sure that we have different kinds of data in that labeling, and we also cover all interesting cases for us. So we might not have 50-50 distribution of handwriting and the images of the textbooks. It might be on some markets, it might be, like more handwriting, and on some markets, it might be just a little of handwriting. But at the end, for the training, it's best if we have the data. It also contains a handwriting and contains different kinds of data, so we can handle it better and it generalizes better. We came up with the self-supervised learning for kind of clustering or unsupervised image classification purposes. And there are these cases that I mentioned that we have the text and the images. Specifically, you can imagine the use case, which is not true use case, but you can imagine that we have an image, the one with some text, not like the question like in Brainy, but like in general, you have some banners from the shop. Generally, there is image and there is text. And let's imagine that you have some method to generate text from the image. And so you have your data, you have image and text, and the text says that there is a shop 24 hours, and there is an image of that shop actually. And what we would like to do, it's to generate the pseudo label for the image based on the text to understand whether it's, for example, a shop or a stadium. And we can leverage then some NLP model. We can reuse BERT or anything like that to do fine-tuning. We can do the zero-shot learning things, so on, to generate the labels. And we can treat them like smooth labels and then just train the model solely on the images. So currently, the most interest to us is that how we can reuse the modalities that are not available during the inference, but to reuse them to generate the labels, so we don't need to label everything.
Right. Thanks a lot. And you mentioned one thing earlier, and you talked about pseudo-labeling being this particular technique to use to overcome this or battle this overfitting and stuff like that. So how did you achieve that in your use case in Braille? Did you have a scenario where, can you give us specific details on the scenario where you were battling overfitting and then, pseudo-labeling came to the rescue at that point?
So in the terms of overfitting, my use case was more or less in the past experience the one with dog collars, and also more with some NLP use cases. At Brainy, we have currently one use case where we are exploring pseudo-labeling possibility to apply. And basically, the reason behind we are tackling with overfitting is that the task that we are solving is very subjective to define, and we struggle with labeling consistency. And also, we don't have a good weak classifier. So we need to handle somehow the class imbalance, where we have not so much images on the class we want to detect. So that's the great case actually for the semi-supervised learning techniques and pseudo-labeling, where we need to leverage all of that unlabeled data.
Cool. And I'll just zooming into this particular one is you're doing this, you're using pseudo-labeling and so forth, but at some point you hit this roadblock, right? What do you do? How do you think about enhancing this technique you're using, or do you just explore other techniques? Because you talked about smaller data sets being a major challenge with using pseudo-labeling. How do you enhance the quality of your data sets? Do you consider maybe synthetic data sets, or can you walk us through that?
Yeah, so we try to be creative with the way how we create data sets. So we don't need really to recreate data like images, because we have so many images. It's better for us, for example, if we are having a label for an image, it's better to search for similar images. We have some pre-trained embedding for similarity, like simple contrastive learning. If we find similar images, we can mark them, as having the same label. That's one thing. The other thing which I like, it's also usually people think about data augmentation as an augmentation of images or text, basically not the targets, but the inputs, right? A few years before, I was doing pose detection, and it was also time consuming to label the pose of human, since you need to label like 12 body joints or something like that. And we struggled also with overfitting. And we had that idea that, if you label the body joint of the pose and you move your label of the body joint just, a couple of pixels, it's basically the same labeling, since you just labeling whole head with single point. And we did a target augmentation. And similarly, you can think on the data augmentation that we're trying to do at Brainy sometimes, that we try to change input images so they reflect different target that we lack actually. And that's also the way how to creatively increase the amount of images in data sets. At the end of the day, it's best just to label your images, and sometimes so that's what actually I'm just doing personally. I'm just labeling more images to improve my model performance or improve my method for sampling more data. It's important to be very creative in the creation of data set, and I believe that creation of data set in the production like environments, like in the commercial setting, is very important, even more important than the training. I think Brainy approach to the machine learning is a very data centric approach, and we try to build all of our software the way that if we just change, if we need to change the data set, we can rerun everything and quickly have the updated model on the new data set on production. So I really believe that that being creative and putting emphasis on data set creation is very important.
Awesome, thanks. And beyond the data set problem, have you found circumstances where some issues kind of affects the efficacy of your pseudo labeling for your image test?
Beyond the data set problems, so I would say that typically connected to the training issue is the overconfidence of the neural network predictions, and
Right.
that's something that that's very hard to tackle, and that's the thing with the confirmation bias. And you can do the mix-up strategies and so on, but at the end of the day, it's very difficult. We actually, like to understand our predictions, whether they make sense. We use also the explainers like Shapley values or the older like Lime, but they're not necessarily always working well with the images. Sometimes they do, sometimes they not. And the overconfidence of the neural networks, even if if you have a good metrics like on your test set, on the validation set for your task, whether it's precision, recall, F1, whatever, it's still not great if you see that your predictions are very overconfident. Something might be wrong there, and it's definitely influences the ability of reusing pseudo labels well.
Gotcha. And I think there's this particular, I don't know how common is it, but it's kind of like, cluster assumption is a necessary condition for pseudo labeling to work. And what do you make of that as that particular phrase itself?
Yeah, so the cluster assumption basically says that the data, when classified, it should be formed in the separate clusters, and the decision boundary. So when you think like similar, like in SVM scenario, decision boundary needs to be in the low region density. And so what they did in the original paper, actually, that was a very interesting experiment on pseudo labeling. So they trained on MNIST dataset, the well-known one, but some experiments were later on reproduced on the CFAR and so on. So it's not only MNIST setting, but on MNIST, they trained the model and they visualized the prediction with TSNE, using TSNE for dimensionality reduction on the plane, on the 2D plane. And actually, the separation of the prediction when it's trained in purely supervised manner, it's not that great. And like when you use pseudo labels, and when you use pseudo labels, the clusters are clearly pushed from ourselves. So there is clear, a clear boundary between the clusters. And that shows that the entropy regularization, which is simply pseudo-labeling loss function, is simply regularizing entropy regularization, which means that we're trying to decrease overlap of classes. And at the end, when you visualize it, it's indeed decreased, and the classes and the clusters of classes are really separated.
Perfect. And in terms of the biases that have you found that this sort of reinforces some certain biases beyond the confirmation bias as well, especially in the self-supervised learning? Or using pseudo labeling, have you found that there are ethical issues with using that? And if there are, maybe you can let us know.
I think the issues are, like they are somehow inherited from the data set you're using. So I don't think it's influenced more by the model or the technique of the model. So if the biases are in the data set, they will be reproduced by the model. So if you want to debias your model, you need to debias your data set.
Awesome. And speaking of data sets as well, of course, we spoke about small teams earlier, being these people that have access to labeled data sets. And of course, we have lots of unlabeled data sets out there, and those are most likely inexpensive to get. So how can they find this balance, especially if it's very crucial for their use case? How can they find this balance between they have this small labeled data sets, but there's a large this amount of unlabeled data sets out there, and they have to use this particular technique? How would you advise that they go about finding that balance and applying pseudo-labeling properly, or even on self-supervised learning? Yeah,
I would advise to, you need to consider obviously what kind of infrastructure you have, what kind of, how much data you actually can train on, what kind of resolution of data for your problem, and what time do you have for that, and whether it's whether you're paying for the cloud, or it's somewhere in your house you have just that your only constraint is the size of the GPU and the time of the training. But when you consider all of that, I would just start with the smallest data set, labeled data set that is actually training something. So it's not working like flipping a coin, but it's actually training. And I would try to, as early as possible, visualize that to see whether indeed there are some clusters created of your classes in the data set, whether they make sense. And if they do start making sense, then there's that part when you can add unlabeled data. So in the original setting, it's done simultaneously, that you're training on the labeled and unlabeled data, but obviously you can just start with the only a small amount of labeled data, see whether it performs just a bit, see whether the visualization makes sense, and then you can do the two-stage training when you figure out that that's the enough data. And if your data is not enough and you don't see any clusters and it's not training, then you simply need to label more at the beginning. And once you're there, then you can start adding up the unlabeled data. You can just start from the beginning your training procedure and try to make it simultaneously. But even if you're training simultaneously, you just start with the training unlabeled part, and the coefficient for unlabeled loss, it's the way that it's 0 at the beginning and then increases linearly until it gets to the final value, and you're still training for some time.
Perfect. And I believe that quite a lot of pseudo-labeling, self-supervised learning is still actively in research, right? And are there sort of particular situations or scenarios where these actually you apply these techniques and then they improve the robustness of your model or your model performance, whether it's at Brainy or even your previous companies? Because we have teams who would want to share this and, hey, look, we could try this out, right? But we need actual numbers to understand, how it helps in sort of in the real world in production. Yeah.
Yes. So in this typical scenario of the pseudo-labeling, when you use the labels from the training model. So in the case of the dog collar thing, our model was overfitting to the way that it was really not deployable, since even if it had good enough performance, for example, for the classification, but the gap between the training set and the validation was huge. So I wouldn't trust that model. And the pseudo-labeling helped in a way that the gap was limited, and the gap was small enough that I saw that it's not overfitting anymore. It was maybe it wasn't perfect metrics, but it wasn't overfitting, so it was started to be deployable. So that definitely helps. And that was in the original settings of the pseudo-labeling when we used the implementation from the original paper, which is very easy rather to implement in any framework, whether you use PyTorch or TensorFlow. And already there are lots of improvements, like to dealing that with the confirmation bias and using mix-up strategy. And also in the original paper, for example, for the pseudo-labels, they do the argmax on the output of the model. So they use hard predictions, and especially in the mix-up paper, they show that the hard predictions are the reasons also for the overconfidence of neural networks. And therefore, there's a whole mix-up or just label smoothing, which helps as a regularizer to improve, to tackle overfitting.
Awesome. And I want to come back to the compute side of things briefly. Are there sort of specific architectures that, you apply at Brainy when sort of using these techniques in terms of your compute architecture? Do you use distributed computation, especially in the data augmentation, which I believe is going to be distributed? Or how do you set up the architecture for both the data processing, which is like a huge deal, as well as the training the models themselves?
Yeah, so we for most of the stuff we use SageMaker. For the experiment tracking, we use Neptune. That's more on the development side, but we track there everything like processing jobs. We try to track everything to just like not miss anything during the creation of data set or anything like that. In the terms of computation, we just use the SageMaker estimators and SageMaker pipelines, and like they both support multi-GPU instances and multi-node instances. So we try to also do the training just on the cluster of instances, where each instance had a multi-GPU. Was a multi-GPU instance. We use mostly PyTorch, and it supports. There's that tool called Torch Distributed, which we use just for running distribution over the PyTorch. But there's also a native SageMaker way to orchestrate that. So we are exploring that also currently, whether it improves something or not. There is also some work to be done, I think, in the terms of optimization, how we use, like in this typical setting is the Horovat algorithm, but there already, in the past, I had some experience with the distributed algorithms that better than Horovat, for example, elastic averaging, stochastic gradient descent, which had actually sometimes in some use cases super linear speed up for the training convergence. So that's something which is also worth exploring in that term, but also requires a bit of custom implementations.
That's awesome. And maybe I'm too picky, but I think, can you walk us through that particular data infrastructure itself? In place, where do you store like all your data sets, if that's exclusive, of course, and how do you actively go about that? You mentioned NVIDIA DALI, which is very crucial for like augmentation, but is there another stack around it that you could share? Are there other stacks? Sorry.
Yeah, sure. I think I can do it in some simplified manner. So generally, we use S3 on AWS for storing data sets. We have built our internal solution for datasets versioning, actually, since we didn't find anything in the space that suited us well enough as of now. We use that solution to obtain data sets whenever we run the job on the SageMaker. We built some of our own CLI to extract the running. So actually, we have the same commands and the same code for running on the local environment, on the EC2, but in the kind of local mode when you're connected via SSH, and that's the perfect setup for a data scientist who works in the cloud. That you had just terminal open, you are connected via SSH, you have that GPU just in front of you to be used, and also running in more reproducible manner via SageMaker. So you can do that via SageMaker estimator, or also as a SageMaker pipeline when there are multiple steps. So typically we are running more production-like training as SageMaker pipeline, so we can have there some pre-processing of images, or we can just have the training pushing to the model registry, which we use also on the SageMaker. When we push something to the models registry, we have some automated job there to evaluate our performance on the holdout set. And if it's all right, if all metrics that you just, like as a data scientist, you look at the run metrics at the Neptune, whether the metrics are okay, then you go to code pipeline, you approve the model, and it's pushed to production automatically.
Awesome. Thank you for sharing that. I think that's probably, I don't think we have any question from the community, Sabine. Yeah?
No, not right now.
Awesome.
Someone did message me that the one question was kind of like asked already that they wanted to ask. So
okay.
Seems like, yeah, we're on top of it.
We're asking the right questions. Awesome. Yeah, I think there's a really good note to sort of end. And I know this particular field is sort of actively being researched, and papers churning out papers and so forth. And are there particular things that you can't that actively being researched right now in self-supervised learning, pseudo-labeling generally, that you can't actively take into production, and you'd want to do that?
Yeah, they are.
Okay.
They are. I mean, you always in that commercial setting, you are kind of limited that you need to balance between risky, not risky things. And in the self-supervised learning is the thing, like the training takes a lot of time and costs a lot. So you need to, you cannot just go put grid search on the parameters and train, like 100 variants of that model, because it's gonna cost like GPT training, like $2 million or something like that. So it's something that you need to work carefully. But generally, using that self-supervised learning approaches, it's something that we definitely want to explore at Brainy, since we have lots of data. And we know that our domain of images is much different actually than ImageNet and even other domains. So for example, from our experience in Vice project, when we are doing object detection for the question layout, we tried to reuse the labeled data on the medical publications, which were labeled actually already for the bunny boxes, or some mathematical papers also. And the problem was that that data was actually much different. And, the solutions which were trained on the data didn't work well. And even reusing that data for sampling purposes, for detecting something on our data, was really random. So it just shows that deep learning at the end of the day is just training some hash maps, which work very well on your particular use case.
Awesome. I think we have a community question.
We do have a community question from Yuri, who may have joined the discussion a bit later. He's asking, what is self-supervised? So Mateusz, would you mind giving a bit of a summary?
Sure. So self-supervised, I would say that's the subset of unsupervised techniques when you don't have labels, but the self means that you use the input image to generate the label. In this use case of simple contrastive learning, to generate the label, you take the image, you do the two augmentations of the same image, you know that this is the same image and that's your label. And if you do the augmentation of two different images and you compare to each other, then your label is that they're not the same images. But basically you generate the labels from your data and you kind of train like in supervised learning, but you don't have that like annotated labels like in supervised learning, but the labels are generated somehow from your inputs.
Mateusz, thank you. And if there are some kind of reading materials, I would appreciate a couple links. Yeah, the reason why I'm asking, we do image embedding and image comparison. Maybe whatever you referring to fits to use case we're trying to solve. We're using pre-trained model, right? When semantic space already built.
Exactly. So you might consider things like simple contrastive learning, SPICE framework, SCAN framework. I think guys can put that on the notes.
It is probably terminology thing. I never heard the self-supervised. But thank you for explanation.
Sure.
All right, thanks, Yuri. And just to kind of wrap things up here, Mateusz, so from your perspective, what would you say is your biggest challenge with MLOps right now?
So my biggest challenge right now is connecting all these steps in the whole machine learning model life cycle. And lots of my challenges right now are like around dataset creation, like from the data versioning part, where we create lots of data sets using different techniques. And that's just one stone to be done. And for creation, you also need automation like SageMaker pipelines for training. You can use SageMaker pipelines for automation of dataset creation. At the same time, the labeling. So how would I know that I have enough data labeled and I don't need to label more? I don't need to label on my own more, or I don't need to pay more the freelancers or MTurk to label more, and it's enough. So some kind of automated active learning techniques could be there are also to be considered. They could be useful in automating your data set creation. So my current challenges in a machine learning model lifecycle are mostly around dataset creation. We are pretty much well organized with the training, pushing to the production, continuous delivery of that. Also, I'm working as I'm officially machine learning engineer, but I work more on the data science side. So the challenges around data sets are currently the most I challenge every day, but also the production challenges for actually detecting when your model starts to perform worse in the absence of labels. So analyzing the predictions shift, the inputs shift. These are also things that I'm currently exploring.
Right. So I'm sure you're not going to run out of challenges to solve anytime soon.
Yeah, I'm not.
Yeah, may I ask you, so in your kind of experience, you're more on a batch side, right? You're not, my feeling, you're not addressing the serving model, right? You not externalize it.
Yeah.
the same here. Yeah, and I'm looking for kind of more use cases, business requirement to serve model instead of constantly processing data. But from a business input, it's not often use case. That would simplify or make something cheaper, but we should be business driven. Thank you.
Thanks.
Right, thanks. And if you have any further questions or any topics for discussion, we can take it to the MLOps community Slack, where we have our guests there from our episodes, and we have Stephen there. And yeah, basically we can continue any discussions there or take up any questions that you did not have the opportunity. So Mateusz, as a kind of like final bonus question, who in the world of MLOps would you like to take to lunch?
Oh, I think there are plenty of interesting people in that world. I would maybe point Mati Zacharia from Databricks, CTO. They are doing MLflow and Spark. So these are pretty interesting solutions. Yeah.
Excellent. So how can people follow your what you're doing and connect with you? Maybe online, you could share.
Yeah, I think it's good to connect with me on LinkedIn and Twitter. I think on both it's just Mateusz Opala, my handle there. So it's the best way to approach me on socials. Yeah.
Great. So thank you so much, Mateusz. It was very good to have you on the show.
Thank you very much. It was a pleasure.
It was very good to hear you share your very solid expertise. And we will be back in 2 weeks on the 20th of July. We'll have Andy McMahon with us, and the topic will be your first MLOps system. What does good look like? So we will see you on socials and in the MLOps community Slack. We have posted the link in chat. Join us there and catch up with any previous episodes as usual on Apple Podcasts or Spotify or wherever you get your podcasts. We will see you very soon. Thanks again, everybody, and take care. Bye-bye.
Yeah. Okay, everyone.
Thanks. Bye.
MLOps Live is brought to you by Neptune AI. Remember that you can join us live at the next event and ask your questions. We run it every other Wednesday, and you can register at neptune.ai/events.
And then make sure to search for MLOps Live in Apple Podcasts, Spotify, Google Podcasts, and anywhere you get your podcasts. Click follow and don't miss any episodes.
Thanks, and see you next time.